Welcome back to channel Bal Vigyan Bharti with Abhilash Sarkar. Recently, we have finished time and work uh, segments. There, we have solved 50 problems shown by describing, analyzing different methods of solving the problems. After giving us some sort of theoretical aspects of that. Now we move on to a subject that will belong to the part of physics that also being demanded. There the demand has came to show some problems by solving by the analytic method or the process that has to be followed. But that is a the subject is belong to a part of a complete subject that is your fluid mechanics. Fluid mechanics basically have two parts, statistic and dynamics. There the part is being requested for solving problem is fluid statistics. So my intention to cover it whole. So I will go with the theory part first, statistics, then I will followed by the problem solving session on that. Then after the second part, dynamics and problem solving. So this way that thing will move. So let me start the first part, that is the fluid statistics. So let me describe the subject as a whole, that is fluid mechanics. Okay. So as it is a fluid mechanics as a whole a subject, it has, you can see a two part. The first part of it is fluid and second part is mechanics. So mechanics, you have quite understand that mechanics as a whole, it related to the statics part of that, when the fluid is in static condition or in equilibrium condition, or a condition where there is no motion, or a motion is such that this has a specific kind of motion where some assumption will be involved. So all that comes under statics part, and the other part is dynamics. So mechanics altogether is a static plus dynamic, and the first part of that on which the things will be discussed is a fluid. So first we have to understand what is fluid. As you know, any matter can stay in three states. We have learned it before also. The three state of matter is solid, liquid and gas. Solid, liquid and gas. So these are the three only state which can exist in universe when matter exists, and that could be in this state. Out of that, fluid as a definition we can say any matter, as we can see these are the state of matter and state of matter, MATTER. This is state of matter, solid, liquid and gas. And any matter which flows. So in a short and simple definition we can say any matter which flows are called fluid. So out of these three we can definitely can tell that solid does not flow. Only the thing we can see flowing with our common sense is liquid. We can see when we will open a tap, water is flowing, that means flowing. Gas means any kind of gas which is being confined in a cylinder. When open a knob, as in your cooking gas, you can see when you open the regulator, it flows and we can burn it. So gas and liquid both can flow, but in case of solid, if we keep a iron you can say ball or something on the floor, it will not flow. It will roll or slide, something like that. As a whole, that body will move, not a way that every part of that will move differently. So when there is a flow, that is only called the fluid. So fluid is only, you can say, for liquid and gas are the fluid. So the first thing is clear. We'll talk about liquid and gas and their mechanics. First part is statistics. Second part is dynamics. So these are the two parts in that we will discuss further. So our part of discussion for the first lecture or the first part of the discussion of first subject, we'll choose the fluid statistic. Okay, so while discussing fluid statistic and with the fluid, we have already known that fluid is all about liquid and gases. Now the second thing, this is the first part. The second thing, there are some criteria or declaration or assumption, whatever you say, that has to be done prior to move on to the detailed discussion. What are those? We will work or discuss only with ideal fluid. So now if it is the declaration, so what is the thing which we understand by ideal fluid? That has to be understood. We will work on or discuss with only the ideal fluid. Now we have to understand the one new term that has came as ideal fluid. So now let's move on to the ideal fluid. So unless and until I specifically say nothing, you have to understand that we are talking about ideal fluid. What are the other aspect of fluid? What could be the other part of the fluid we can describe? That is the practical fluid or the real fluid. So whatever ideal fluid by which it is being defined, the same criteria or the we can say the same criteria cannot be achieved in practical fluid or real fluid, or the characteristic that I will define the ideal fluid, the characteristic in practical or real fluid will be just opposite. Okay, so ideal fluid have three different criteria. Okay, so what are those? First, the first one is it is incompressible. It is incompressible. What does it mean? Let me assume that a fluid is kept in a container, a solid container. This is a solid container, and there is a fluid being kept. For example, if you can see it, water inside it. Water is a liquid and it is also a fluid. So it will take the shape of the container as well as it will occupy some space in it, some volume, because water is a specific volume as all liquid has. So water will contain some volume here. Now above it, if I keep a piston, like that, I want to put a force. If I put a force, means if I put a force there on it, on the total surface, where I will not allow any liquid to move out or release from the side of the piston. It is a tight packed, and I will try to push the liquid down. I will not able to do it. That means it is incompressible. That means there will not be any movement there. No movement can be seen in the piston. What does it mean further? That means if the piston is not moving, so whatever volume it is occupying, it will remain the same volume. So volume will be same, volume won't change, because you will not able to change the cross section of the container. Container is so rigid, you cannot even move a single micron and deform this container, that is so solid. So when you try to move piston, unless and until it is deformed, it won't change the cross section. So what is the possibility? It can only compress and move down. So if it is not happening, so that means there is no change in volume. So the next part of it is no change in volume. We can say that. Okay, up to this is okay. Now what else we can say? Now if I see the mass of the fluid, there is mass we cannot create. Whatever mass there inside this container will remain. And what is the mass? Volume into the density. If I say it, volume into density, this is by definition is the mass of any object, or means on any matter. For any matter, volume into the density, it will give its mass. This is mass. Okay, MASS, mass. Okay. Now if mass is constant, because in this inside, if I am not putting any further same liquid which is occupying here, or not I am bringing out something, because I am not I am restricting this to flow out. This is so compact. I am not allowing even a small fraction of water outside it. I am not allowing the leakage. So whatever mass there inside that thing, it will be same. Now mass is constant. If mass is constant, then volume into density also to be constant, because this left hand side has to be equal to right hand side. Now in left hand side is constant, right hand side volume I cannot change. So what else I can change? I cannot change any other thing, because if anything changes, all will be affected. So density also doesn't change. So the next conclusion, if it is incompressible, no change in density. So I can conclude, for ideal fluid, my assumption should be no change in density, and that would be our base of discussion. Wherever I will discuss about the ideal fluid, we'll assume there is no change of density. Okay, this is first assumption. Fine. Moving on to the second assumption, non-viscous. Now what does it mean? Now again we will talk about the three state of the solid, state of the matter: solid, liquid, and gas. Now if we can see any solid matter to move, if I roll this chalk on the board, as a whole this complete chalk is rolling, not that the each particle or the layer is moving differently. Okay, it is not moving like that, it is rolling completely. So that means when a liquid is said to be viscous, that means our assumption is such that any fluid, wherever it is flowing, it will flow layer after layer. There are in so thin layer, because this is just an assumption, because when a liquid is flowing, it won't flow as a solid body. Just like if I say that ice cube is there, if I slide it on the floor, ice cube will hold total, it will flow. But if I pour a water inside into any floor, it will flow wherever it is starting. There the thickness of the flow will be high, and when it is coming down to the surface, it will be less. So that means if it is a viscous one, everywhere the cross section of the flow will be same. So I cannot say that water is viscous, whereas if I say the ice, it will flow with a intact shape, at least somewhat. If I can able to maintain the temperature, it won't melt and it will flow of its own. Is a complete body, as a complete body. But whereas if I pour water when it is flow, and after pouring on the floor, it will be thinner and thinner, and the end it will be very thin. More the distance it will travel, there is a very less amount of water it will flow at the end. So constantly the layer after layer it is flowing. Why? Because the surface it is touching with that, there is a friction force which is restricting the flow. But when it will move up, layer after layer, friction force is less, so there will be more velocity on the up and less velocity, so it will be dragged down. So slowly this will be lesser and lesser, like that. But this is a different factor altogether. But to understand the viscous flow, if it is non-viscous, that means no relative motion between the layer. That means no relative motion between layers. Just like solid flows all as a body, so there is no relative motion between the layers. So that means there is no we can say that means there is you can say that will act like a single body. No relative motion means all layers are moving same way. So that is only possible if I say the liquid, there is a same friction between the layers, that is not allowing the layer to flow one to another, and such as there is the friction is there with the solid body, and the same it is being transmitted to the all layers. So that is just like a solid body is moving. So if in case a liquid in that state, when it is moving just like a solid body, then it is said to be a body is a non-viscous. Or else the for the simple way, if you have to understand, there is no relative motion between the layers. If we assume the fluid are made of different layer, there is no motion between the different layer. There is no relative motion, means one layer is going out of another, it is not happening. So it is a simple body, it is flowing just like a solid body always. So that is the assumption. So that means there is no relative motion between the layer. This is the second assumption. Third assumption, no rotational motion. Or rotational flow, you can say. Because whenever we discuss, we may discuss different kind of container which may have some curve in it, like that. So wherever I will even I will discuss the statics, where there may be a fluid column is moving from here to here, it won't be affected by this curve, because curve motion, whenever it will come, I have to take it in a different way than the linear motion. But everywhere, even though it is moving through the curve, it won't consider, we will not consider the rotational motion. We always will consider the linear motion, and that too all fluid will move as a single body, not that differently it will moving. It will move. If it is moving the total layer, if I consider to be this one, after some while if it is being moved, the complete layer, the length of the layer will move together. So this will be the assumptions. There is no rotational motion. So with this assumption, this ideal fluid assumptions and all this criteria, we will move on to the subject. Okay. So the first you can say the first character or the first you can say element of this statistics which will come will be named as pressure. Okay. Now if I want to define pressure, before than that I want to make you understand what is exactly the pressure. Okay. And this pressure is only will be defined for fluid. Okay. And that has to be understood with your common sense, and practically that has to be understood. Theoretically I am trying to make you understand what is all about. Now let's say I am having this uniform container with some fluid, okay, in it. Okay, fine. So what do you understand by seeing it is that this is a round shape container. The bottom is round shape. I assume it is a cross section A. The height of the fluid is H. Now if I say what are the forces being applied onto this surface, ultimately will be the, because as you know we are living in an atmosphere where air is always present, and air is exerting a pressure downward due to that gravitational force, everything being pulled towards the center of the earth, and due to that whatever is surrounded this earth is always vertically downward, is acting vertically downward, so as that the air pressure also working on the surface of this liquid as it is working on any surface. Okay. Now this is exerting a pressure, let's say this is F0, and apart from that whatever the liquid is there inside, it has some weight, and that weight is being exerted as a force on it with this, because this is the weight of the liquid is there in the container, and that is acting on the bottom of the container, because this will not act outside, because this is the inside the container, and this is the total weight of the liquid plus the force is acting on the surface of the liquid. All together this is the complete force. Let's say F is acting on this container. Okay. Now if we can say that this is the area and this is an uniform container where cross section is same always everywhere, so whatever pressure, whatever force is being created here, same will be transmitted vertically, because this is, we are talking about the perpendicular force, vertical forces. Okay, so whatever vertical force is acting on it will be transmitted through this liquid column to the base actually, because this will be acted on the this column, and this all together this force plus this force will ultimately be exerted on the bottom of the, this is the total force perpendicular acting on the surface. So now if perpendicular, if I say the force acting is the atmospheric pressure F0 plus the weight of the liquid column. So now if this is A, so if I want to calculate the unit force, let's say this is A surface, this is B surface. Unit force on B is how much? F0 by the area. Unit force means what? Force per unit area. This is unit force means force per unit area. This is the force acting on B surface. If I say this is the horizontal line on which the atmospheric pressure, this is just the top surface of the liquid, of the fluid on which the air is exerting. Air is always present, air is giving the same pressure, means it is exerting its weight everywhere on the surface. And now if it is a part of the force, if I want to consider, this is F0 you can consider, and this is exerting on the cross section of A at B. Now going in below, in this surface, in A surface, unit force on surface B, on surface A is how much? The total vertical force by A. You can say that this is the unit force per unit area is the force. So this is, so now if I put it here, or else if I divide it by A altogether plus W by A, this pressure is nothing but the force per unit area. This is the definition of the pressure. Now why I have taken so much time to describe the pressure? Because if I say directly here, you won't understand what is pressure exactly. So I thought it will be better if we go by the force and understand how that pressure is being related to the force acting on the fluid surface. So force acting on A surface, this is A, I will name it A rather, not vertical, because vertical you understand all the vertical force. We are not taking any force which is coming, because everywhere there is a force. I am not considering all the force coming elsewhere. It is the only the vertical force acting on the surface of the fluid contained in a container. Okay, because fluid cannot be kept anywhere, it has to be contained in a container, then only it will take the shape of the container. So as we have considered, this is a container on which everywhere that air pressure is there, air load is there, and here air also loading on the surface. So this is the pressure at point A, and that at B is PV, that is you can say FO also, because this is the pressure which is everywhere on the floor, on our body, everywhere this same, this PV means this is nothing but the air pressure or atmospheric pressure, you can say atmospheric pressure, you can name it atmospheric pressure, plus W means M into G by A. Okay, now what is M? M is equal to V into rho, that we have already described. Mass is equal to volume into density. Rho is defined by the density, or else I will write one line more, volume into density, and volume is defined by V and density is by rho. Now mass is equal to volume to density. Now further, if I consider the volume of this liquid, because mass I am consider for the fluid. So volume of the fluid is this one. Now volume of the fluid is what? Cross section into the height. Okay, so now it is A into height into rho. Okay, now I will rub it. Now this become P at A is equal to P atmospheric, I will write, plus M into M means A into what I got here, H into rho into, and G was there, G by A. Now if I cancel it out, A I will get P atmospheric is equal to PA is equal to P atmospheric plus H rho and G. Understood? So this is the relation of pressure at any point in the container with atmospheric pressure and the height of the fluid inside the container, the rho of the fluid inside the container, and the G is the gravitational force. As of now, you just understand this is G gravitational force. Now later some more concept will come where we'll talk about this G, but as of now you understand this G is belong to the G which is caused by the gravitational pull on this liquid. So H is the H height of the fluid, gravity of the fluid, and G is the gravitational acceleration. Okay. So now the condition of this is the liquid or the fluid inside it, fluid is in static condition. Okay. So this was the assumption before prior to discuss this. So the fluid is not influenced by any, not influenced by any external energy. That means its state is not being disturbed by giving energy or bringing down or bringing out any energy out of the system. This is in static equilibrium. This is in static condition with consumed energy here. Okay, I am not putting any energy inside or not bringing any energy out of it. So this is the condition where this equation will can be established. P pressure at in this container at any point will be the P atmospheric plus the height of the fluid from the surface from where the atmospheric pressure is considered. That means PB. That's why I have taken initially B, not the atmospheric. The reference will be the open surface on which the atmospheric pressure will be exerted directly. From that point, I will consider the height till the point where I want to get the pressure. So if I want to get the pressure here, so I need to have that height, whatever is there, then only I can get this value here itself. Let's say this is A dash. Now I will get A dash if this height H dash is known. Okay, so this will change accordingly to the reference line of this. Okay, so this I have established. Now another concept. Now this pressure, now as we understand that pressure is being created, and that is created due to the force exerted on the liquid. Okay, now if I forget about this part right now, the pressure exerted on the floor of the container, rather if I only consider this atmospheric force on the surface of the liquid, how will it behave inside the liquid? Okay. Declaration is that this pressure will act into this liquid in every direction. The pressure being created due to this atmospheric pressure, if I only consider this atmospheric pressure, it will act in any point of the liquid in all direction, so this will act in this direction, this will act in this will act in every direction, it will work. But and that can be understood practically if we consider a container with multiple opening, okay, in any direction, if you consider any opening, let's say this is a straight opening, this is a tangential opening, this is a downward opening, this is a bottom opening, this is again a horizontal opening, this way. And if you put a pressure gauge here, is a valve, if you put a valve here, then after a pressure gauge here, everywhere valve and pressure gauge, okay, this valve and pressure gauge, valve and pressure gauge, okay. Now without disturbing this liquid, you open this valve slowly, you will get whatever value of pressure here, you will get the same pressure here, you will get the same value of pressure here, you get the same pressure of air, you will get the same pressure of air, unless and until you don't change the condition of this container with any respect, you will get all pressure in all direction are same. So that means whatever force is exerted on the surface, it will be transmitted to the liquid equally in all directions, okay. This is practically can be understood or seen. If I say it, you will not able to believe, but you have to believe it. This is the practically being done, then only it has said pressure on any fluid is in static condition is always same in all direction, okay. So from there we can say pressure has no direction, you can say the pressure has no direction, or else pressure is a scalar. Understood? So pressure is a scalar. So I will stop it here. You just go through this session, and I don't know whether you have got my point, or if you have any doubt, kindly comment, because I will move in the next session basis of this concepts. So unless you understand this concept, you will not able to correlate with my statement or my you can say the lecture the way I want to communicate to you, okay. So it's better to go through this, try to understand. If you have any doubt, just ask me on the comment section, so that I can again, if it is needed, I can explain or discuss it about this part again, and I can move further, okay. So till now, with this hope, I am just ending this session, and in the next session I will discuss some of the more aspects of pressure, because pressure has to be understood to understand this statistics part. So I will try to create more environment. If it's not possible for me to show you the practical examples or practical exercises, but I will try to make you understand some of the aspects which may be not easy to accept, but you have to accept it I will try to make you what I can say, understand the concept I will deliver. So that is most important. Once you will understand that, later part will not be very tough for you to carry on. So as of now, I am just ending this session. So thank you for now.